The Mediterranean Sea occupies a unique position in the geography of the planet. With its approximately 2.5 million square kilometers of surface area and a length of just over 3,700 kilometers from west to east, it could pass for a sea of conventional size. However, its physical, geological, and hydrological characteristics make it a system with no real equivalent anywhere else in the world. In terms of average depth, the Mediterranean reaches about 1,500 meters, although in certain areas it descends to levels that for a long time remained beyond the reach of exploration. Its connection with the Atlantic occurs exclusively through the Strait of Gibraltar, a passage barely 14 kilometers wide at its narrowest point and about 300 meters maximum depth at the submarine threshold that crosses it. This single conduit transforms it into a semi-enclosed basin, with extraordinary hydrological consequences. The evaporation rate of the Mediterranean far exceeds what it receives through precipitation and river inflows. The rivers that flow into it, among which the Ebro, the Rhone, the Po, the Nile, and several Balkan and Turkish river systems stand out, do not compensate for the volume that evaporates into the atmosphere. This generates a negative water balance that forces the sea to import Atlantic water constantly. Through the Strait of Gibraltar, a double superimposed current circulates. Surface Atlantic water, colder and less saline, flows eastward, and deeper Mediterranean water, warmer and much more saline, flows out into the Atlantic along the bottom. This thermohaline circulation turns the Mediterranean into a natural laboratory of oceanographic processes that scientists still do not fully understand. The average salinity of the Mediterranean ranges between 37 and 39 per thousand, values significantly higher than the global ocean average, which is around 35 per thousand. In the eastern basin, especially in the Levantine Sea and the southern Adriatic, salt concentrations reach even higher values. This difference in density is precisely what drives the deep outflow current through the Strait of Gibraltar, a mechanism that has functioned almost autonomously for millions of years. The Mediterranean is divided into two main basins, separated by the Sicilian-Tunisian threshold, the submarine ridge that connects Sicily with northern Tunisia. The western basin, smaller and generally less deep, includes the Ligurian, Tyrrhenian, Balearic, and Alboran seas. The eastern basin, more extensive and complex, includes the Ionian Sea, the Adriatic, the Aegean, the Levantine Sea, and the central Mediterranean. Each of these subbasins has its own circulation, its own water masses with differentiated thermal and saline characteristics, and its own submarine morphological features. The Mediterranean seafloor is not a uniform plain. It is crossed by ridges, sedimentary basins, submarine canyons of colossal dimensions, and active volcanic reliefs such as those concentrated around the Aeolian Arc and the central Mediterranean. The Empedocles submarine volcano, in the Strait of Sicily, partially emerged to the surface on several occasions throughout history, generating the ephemeral island of Ferdinandia, which since 1831 has appeared and disappeared beneath the waves on different occasions. The Mediterranean climate, with its hot, dry summers and mild, rainy winters, is not independent of the sea that gives it its name. The body of water accumulates heat during the summer months and releases it slowly in autumn and winter, moderating coastal temperatures and conditioning precipitation regimes. Autumn storms in the western Mediterranean, known as gota fria or dana in Spanish meteorological literature, are a direct consequence of the contrast between the still warm sea and the cold air descending from the north at that time of year. In October 2024, one of these storms discharged historic rainfall over the Valencian community in just a few hours, with devastating consequences for the region. In the Ionian Sea, southwest of the Greek island of Kefalonia, the seafloor descends to depths that for decades challenged underwater cartography. The Hellenic Trench, The deepest oceanic depression in the entire Mediterranean reaches at the point known as the Calypso Deep, a depth of 5,267 meters. This figure, verified with millimetric precision only in recent times, places the Mediterranean in a range of depths that we normally associate with major ocean basins. The Hellenic Trench extends in a northwest-southeast direction for about 1,200 kilometers, following the subduction arc where the African plate sinks beneath the Eurasian plate. It is precisely this tectonic dynamic that has shaped one of the most complex submarine morphologies in the entire Mediterranean, with multiple internal basins, steep escarpments, and reliefs that change radically in scale over distances of just a few tens of kilometers. The Calypso Deep owes its name to the sea nymph of Greek mythology, daughter of Atlas, who, according to the Homeric account, detained Odysseus for 7 years on the island of Ogygia. The choice of name symbolically connects the most inaccessible depth of the Mediterranean with the imagery of a sea that for centuries was the center of the known world. However, beyond the name, the deepest point of the Mediterranean holds scientific questions of the highest importance. For a long time it was assumed that the abyssal floors of the Mediterranean would be almost devoid of life. The combination of extreme pressures, low temperatures, and scarcity of nutrients seemed incompatible with complex ecosystems. That assumption has been gradually corrected by oceanographic expeditions, which, since the late 20th century, have begun to explore the depths of the Hellenic Trench with unmanned vehicles. The results have been surprising. At depths greater than 4,000 meters, communities of polychaetes, holothurians, ophiuroids, and isopod crustaceans have been identified inhabiting the abyssal sediments. The presence of these communities suggests that the Hellenic Trench is not a biological desert, but a functionally active ecosystem, although extremely slow in its energy and reproduction cycles. Biomass decreases sharply with depth, but does not reach zero even in the most remote points. One of the particularities of the Calypso Deep from the perspective of chemical oceanography is the concentration of organic matter in deep sediments. The Mediterranean, being an almost closed basin with relatively slow exchange of water masses with the Atlantic, accumulates in its abyssal floors sediments that record climatic and oceanographic changes of the last millions of years. Sediment cores extracted from these depths contain alternating layers of sapropels, sediments rich in organic matter that form under conditions of oxygen deficit, and carbonate sediments typical of periods of greater bottom ventilation. Mediterranean sapropels are markers of global climatic events. Each of these dark layers in the sedimentary record corresponds to a period in which the eastern Mediterranean experienced conditions of low surface salinity, possibly linked to increases in the flow of the Nile and other rivers during periods of greater precipitation in the Sahara and the Near East. The last large-scale sapropel formed approximately 6,000 years ago during what paleoclimatologists call the Holocene climatic optimum. Exploration of the Calypso Deep has also revealed the geological complexity of the Hellenic Arc. The area is seismically active, with earthquakes generated both at the subduction interface and along intraplate faults that cross the ocean floor of the trench. In August 1953, a catastrophic seismic sequence destroyed much of the Ionian islands of Kefalonia, Zakynthos, and Ithaca, causing more than 800 deaths and displacing tens of thousands of people. The seismic mechanism of that event was directly related to the subduction dynamics that shape the Hellenic Trench. Approximately 5.96 million years ago, the Mediterranean disappeared. Not completely, and not instantaneously, but in geological terms, what occurred was one of the most drastic oceanographic events ever experienced by our planet. The Atlantic connection, which until then maintained the level and salinity of the Mediterranean within habitable ranges, gradually closed as a result of tectonic uplift in the Betic and Riphean regions. the territory that today corresponds to southern Spain and northern Morocco. When the Betic and Riffian marine corridors were definitively sealed, the Mediterranean became isolated from the Atlantic. The consequences were immediate on a geological scale. Without renewal of Atlantic water, evaporation began to exceed inflows and the level of the inland sea began to fall. Salinity skyrocketed. Marine ecosystems collapsed across much of the basin. Organisms that could not adapt to conditions of extreme hypersalinity perished or retreated to the few environments where fresh water from rivers still reached. The period of maximum desiccation, which geologists call the Messinian salinity crisis, culminated in a situation difficult to imagine. The Mediterranean became an evaporation basin with the water level several kilometers below global sea level. The most widely accepted reconstructions currently estimate that the western basin dried out almost completely, accumulating on its floor sequences of salts, gypsum, and halite hundreds of meters thick. In the eastern basin, the situation was somewhat different. The greater depth of the Hellenic Trench and the fluvial inputs of rivers such as the Proto-Nile and the Proto-Rhone maintained residual basins of hypersaline water. The evidence of this extraordinary event is multiple. Perhaps the most spectacular are the large submarine canyons that European rivers carved in their lower courses during the period of desiccation. The Rhone excavated a canyon more than 900 meters deep that is now buried beneath the sediments of the river delta. The Nile, on its course toward the desiccated eastern basin, carved similar structures. These paleo-channels, detected through reflection seismics, constitute an unequivocal geological signature that the level of the Mediterranean remained for a geologically prolonged period far below global ocean level. The second major piece of evidence is the evaporitic record itself. Messinian sequences of salts and gypsum outcrop at the surface in many parts of the Mediterranean basin, in Sicily, in Spain, in North Africa, and in the Near East. The total accumulation of salts on the Mediterranean floor during this period is estimated at several million cubic kilometers of evaporites, a volume equivalent to extracting nearly all the dissolved salt in the present Mediterranean several times over. The end of the Messinian crisis came approximately 5.33 million years ago, in what is known as the Zanclean Flood. At some point in the Gibraltar corridor, the Atlantic Ocean found or created a passage and began to pour water into the dry basin. The most recent numerical simulations suggest that, once the breach began, the process was catastrophic in geological terms. The most extreme estimates suggest that the Mediterranean could have been refilled in less than 2 years through a cascade of inconceivable dimensions, with flow rates several orders of magnitude greater than the largest waterfalls that exist on Earth today. The question of whether the refilling was gradual or catastrophic remains a matter of scientific debate. Some models propose a two-phase scenario, an initial relatively slow flooding that restored a shallow and partial Mediterranean, followed by a second catastrophic phase that completed the refilling. Others argue that the transition was practically instantaneous from the beginning. Sedimentary records still do not allow a clear distinction between both scenarios, because the very sediments that could reveal the speed of the process were largely destroyed or disturbed by the violence of the currents that accompanied the flooding. The evolutionary implications of the Messinian crisis are equally profound. During the period of isolation and desiccation, populations of Mediterranean marine organisms were separated from their Atlantic counterparts for millions of years. Some became extinct. Others evolved independently in the residual hypersaline basins. When the Mediterranean refilled, it was recolonized mainly by Atlantic organisms, but certain surviving lineages with a long history of isolation left their mark on the sea's present biodiversity. The Posidonia seagrass, the Mediterranean sea urchin, or certain populations of flatfish possess genetic peculiarities that marine biologists link to that period of isolation. In the great oceans, oceanic gyres are gigantic structures that circulate for decades across basins thousands of kilometers in diameter. The Mediterranean, with its much smaller dimensions, cannot host structures of that size, but it generates its own equivalents in scale, known as mesoscale gyres, or, in English language oceanographic literature, eddies. These whirlpools of water, with their own structural coherence, have diameters ranging from 50 to 300 kilometers and can persist from weeks to several years. The most studied Mediterranean gyres are the Alboran gyre in the Western Basin and the set of eddies that characterize circulation in the Eastern Mediterranean. The Alboran gyre is an anticyclonic structure that forms in the basin of the same name, located between the Strait of Gibraltar and the Western Mediterranean, and is directly related to the dynamics of the jet of Atlantic water that enters through Gibraltar. This relatively cold and less saline surface water jet interacts with denser Mediterranean water and generates instabilities that give rise to persistent eddies. In the Eastern Mediterranean, mesoscale circulation is particularly complex. The Rhodes Gyre in the northeastern Mediterranean and the eddies of the central Mediterranean and the Levantine Sea form a system whose dynamics change with the seasons and from year to year. These gyres are more than simple oceanographic curiosities. They concentrate nutrients, affect plankton distribution, and condition fishing patterns throughout the region. One of the most striking consequences of gyre dynamics in the Mediterranean is the formation of lenses of water with thermal and saline properties distinct from their surroundings, which float at intermediate depths for prolonged periods. These structures, called meddies, when they involve Mediterranean water that has exited through Gibraltar into the Atlantic, or similar structures within the basin itself, can transport water with very specific physico-chemical characteristics for years across hundreds of kilometers before gradually dissolving through mixing with the surrounding water. The study of Mediterranean mesoscale gyres has gained special relevance in the context of climate change. Systematic measurements of recent decades show that the Mediterranean is warming steadily at a rate that exceeds the global ocean average. This warming affects the formation of dense water in deep convection basins, mainly in the Gulf of Lion and in the Adriatic, where water sinks to the bottom in winter as a result of surface cooling. If temperatures continue to rise, deep convection processes will weaken, altering Mediterranean thermohaline circulation with consequences that are still difficult to anticipate for ecosystems and the biogeochemical cycle of the entire sea. Another of the most counterintuitive phenomena occurring in the Mediterranean is the existence of true rivers that flow along the seabed. These are not metaphors nor ordinary currents circulating at great depth. They are dense and coherent flows of water that move along the ocean floor following submarine channels and valleys, exactly as a river would on land, except submerged under hundreds or thousands of meters of seawater. The most spectacular example of this phenomenon was documented in the Strait of Gibraltar. When hypersaline Mediterranean water exits through the strait into the Atlantic, it does not immediately disperse in the Atlantic water column. For a certain distance, it flows as a coherent river over the sill of the strait, descending along the Atlantic continental slope toward the depths. Its greater density, a consequence of its high salinity, keeps it attached to the bottom and separates it from the lighter Atlantic water that circulates above. This Mediterranean outflow can reach speeds of several meters per second in the sill area, values comparable to those of moderate-flow continental rivers. Within the Mediterranean itself, turbidity channels are the morphological expression of similar processes. Turbidity currents, generated by the destabilization of sediments on continental slopes, flow along the bottom, sweeping suspended material and carving channels that can extend for hundreds of kilometers. The Western Mediterranean Turbidity Channel, which begins on the continental margin of the Gulf of Lion and extends toward the central Mediterranean basin, is one of the longest known in any inland sea on the planet. In the eastern Mediterranean, there is another related phenomenon, hypersaline brine that seeps from the seafloor at certain points in the basin. In the region of the eastern Mediterranean basin, especially near Messinian salt domes, seawater filtered through sediments becomes loaded with salt until it reaches concentrations several times higher than normal seawater. When this brine emerges onto the ocean floor, its extreme density makes it practically immiscible with the surrounding seawater, and it flows along the bottom like a liquid within a liquid, forming brine lakes and rivers that possess an interface almost as sharp as that, separating the water of an ordinary lake from its atmosphere. Mediterranean brine lakes, such as Lake L'Atalante or Lake Midi in the eastern Mediterranean, were discovered in the 1990s during exploration campaigns with unmanned vehicles. Their waters, with salinities that can exceed 330 per thousand, that is, almost 10 times saltier than normal seawater, are anoxic and practically toxic to conventional life. However, microbiologists have found at the interface between the brine and normal seawater communities of extremophile microorganisms that constitute true biosignatures of environments without equivalent on the planet's surface. Some scientists consider them useful analogues for imagining what forms of life might inhabit the subsurface oceans of moons, such as Europa or Enceladus. The Mediterranean has been the scene of more continuous maritime traffic than any other sea in the world for at least 3 millennia. Phoenicians, Greeks, Carthaginians, Romans, Arabs, Venetians, Genoese, Ottomans, and dozens of other maritime powers crossed its waters with commercial and military fleets of varying sizes. The accumulated result of storms, battles, navigation errors, and accidents of all kinds is an underwater archaeological inventory of extraordinary richness. It is estimated that the Mediterranean seabed holds more than 10,000 identified or suspected shipwrecks, and probably many thousands more that have not yet been located. One of the oldest known shipwrecks in the Mediterranean is the so-called Uluburun wreck, found on the Turkish coast off the cape of the same name at a depth of 44 meters, and excavated between 1,984 and 1,994 inches, 11 successive campaigns. The vessel, dated to around 1,300 BC, carried an extraordinarily varied cargo that includes Cypriot copper ingots in oxide shape, tin probably from Afghanistan, terebinth resin in Canaanite amphorae, African ebony, ivory, glass objects, gold and silver jewelry from different origins, and bronze weapons of Egyptian, Mycenaean, and Syrian typology. The diversity of the materials makes the Uluburun wreck a direct window into international trade in the Bronze Age, revealing connections between cultures of the Near East, Egypt, the Aegean, and the central Mediterranean that terrestrial archaeology could scarcely infer. In Greek waters, the Antikythera wreck remains one of the most famous of the ancient world, although not for its conventional cargoes, but for the artifact it carried. Discovered accidentally in 1900 by sponge divers, the wreck dates to approximately 70 BC and carried, among bronze and marble sculptures and everyday objects, the Antikythera mechanism, a bronze device with at least 82 preserved fragments that, after decades of research, has proven to be an astronomical calculator of a mechanical sophistication unparalleled until the Renaissance. The mechanism could predict eclipses, calculate the positions of the sun and the moon, and track the cycles of the Greek calendar and the Panhellenic Games. Its mere existence rewrites the history of precision engineering in the ancient world. The 20th century added new categories of shipwrecks to the Mediterranean underwater inventory, now made of steel and mechanically propelled. During the two world wars, the Mediterranean was a theatre of intense naval operations. The sea around the island of Malta, the Strait of Sicily, the Strait of Messina, and the waters of the Aegean preserve on their seabeds. Dozens of warships and merchant vessels sunk between 1,914 and 1,918, and several hundred between 1,940 and 1,980. 945. Many of these wrecks have become specialized diving destinations. The Italian battleship Regina Margherita sunk in 1,916 inches, the Adriatic, with more than 650 victims by an Austrian mine, or the cruiser HMS Gloucester, sunk in 1941 by German aviation off Crete, with 722 dead, are just two examples of the enormous number of military vessels that rest on Mediterranean seabeds. Some naval disasters in the Mediterranean had consequences that transcend the immediate human tragedy. In January 1954, the British tanker World Concord broke in two in the Gulf of Lion during a storm, spilling thousands of tons of oil. It was one of the first documented episodes of massive maritime pollution in the Mediterranean, although public awareness of these phenomena would take decades longer to consolidate. In subsequent years, oil spills from tankers such as the Urquiola off La Coruña in 1976 or the Patmos in the Strait of Messina in 1985 polluted extensive coastal areas and caused ecological damage, whose full assessment is still debated. The catastrophe of the ferry Jan Heuelius, sunk in the Baltic Sea in 1993, or that of the Moby Prince in the port of Livorno in 1991, where 140 people died in a fire on board that was initially mistaken for an atmospheric phenomenon, illustrate the persistence of maritime risk even in the modern era. The Moby Prince, in particular, gave rise to one of the most complex judicial investigations in Italian maritime history, with hypotheses ranging from human error to the possible presence of an unidentified military vessel in the area of impact. But the level of the Mediterranean has not always been where it is today. During the last glacial maximum, approximately 20,000 years ago, global sea level was about 120 meters lower than today. The Mediterranean coasts of that period extended several kilometers farther out to sea than today's. The continental shelf, now covered by shallow waters, was dry land inhabited by Upper Paleolithic human populations. When the ice melted and sea level rose progressively over millennia, those coastal areas were submerged, along with everything their inhabitants had built upon them. Mediterranean underwater archaeology has begun to explore these flooded territories with increasing systematicity. On the coasts of Israel, divers from the University of Haifa have documented the site of Atlit Yam, a submerged Neolithic village at depths between 8 and 12 meters and dated to around 7000 BC. The preservation is remarkable. Stone structures, wells, human remains, bones of domestic animals, and carbonized plant remains have been identified, constituting an almost perfect snapshot of daily life in a community devoted to fishing and agriculture at the moment when rising sea level forced it to abandon its homes or simply covered them. Atlit Yam is currently one of the best preserved Neolithic settlements in the eastern Mediterranean, although most of its extent remains unexcavated. On the Italian coasts, the phenomenon of bradyseism, that is, the slow sinking and uplift of land linked to the volcanic activity of the Phlegraean fields, has submerged part of the ancient Roman city of Baiae beneath the waters of the Gulf of Pozzuoli. Baiae was during the 1st century BC and the 1st century AD one of the most frequented thermal and leisure destinations for the Roman elite. Villas, baths, temples and port facilities were built along a coastal strip in which bradyseism gradually caused subsidence. Today, at depths between 2 and 15 meters, divers can visit paved streets, mosaics of white and black tesserae almost intact, fallen columns, and the outline of building plans that 2,000 years ago were frequented by figures such as Julius Caesar, Augustus, Nero, or Cicero. The ancient city of Alexandria, founded by Alexander the Great in 331 BC, has in recent decades revealed its submerged parts in the Mediterranean Bay that bathed the ancient Ptolemaic capital. The expeditions of the team of Jean-Yves Empereur and Franck Godillot have brought to light colossal sculptures, granite blocks with hieroglyphic inscriptions, capitals and columns that belonged to buildings of the Ptolemaic city, and even possibly to the area where the royal palace of the last Hellenistic pharaohs was located, including Cleopatra VII. The search for the exact location of the tomb of Alexander the Great, which tradition places in Alexandria, overlaps with this landscape of submerged and non-submerged remains, making the area one of the greatest archaeological enigmas of the Mediterranean. In Greece, the Bay of Pavlopetri off the coast of Laconia constitutes another exceptional case. Pavlopetri is an underwater city dated between 3000 and 1100 BC, that is, corresponding to the Cycladic, Minoan, and Mycenaean cultures. Its structures are visible at very shallow depths, and surveys using side-scan sonar have revealed an urban layout with streets, buildings of differentiated function, and possibly a water management system. It is the oldest known pre-Hellenic submerged city in the eastern Mediterranean. Hypotheses of future discoveries are the subject of ongoing debate in specialized circles. Some researchers consider that the underwater continental shelf of the North African and Levantine Mediterranean, scarcely explored compared to European coasts, could harbor sites of importance comparable to or greater than those already known. The combination of dense coastal populations over millennia, post-glacial sea level rise, and the relative scarcity of systematic research creates conditions for underwater archaeology to yield major surprises in the coming decades. The hypothesis of a city or set of large-scale structures in deep Mediterranean waters, which periodically circulates in general media with references to Atlantis or lost civilizations, currently lacks support in the available oceanographic and archaeological records. The bathyal depths of the Mediterranean are essentially sedimentary and do not preserve conventional archaeological structures. However, the possibility that little-explored continental shelves, especially along the North African coasts and in the central Mediterranean, contain remains of now submerged settlements is entirely plausible from a geological and historical point of view. On the 17th of January 1966, at 10:22 inches the morning local time, a United States Air Force B-52 strategic bomber collided with a KC-135 tanker aircraft during an in-flight refueling maneuver over the southeast coast of Spain, directly above the town of Palomares in Almeria. The 4 crew members of the B-52 died, as did 3 of the 4 crew members of the KC-135. The B-52 was carrying 4 B-28 hydrogen bombs, with a design yield of 1.45 megatons each. All 4 bombs fell over Spanish territory and the adjacent waters of the Mediterranean. 3 of the bombs were recovered on land within a relatively short period. 2 of them had experienced detonations of the conventional explosives surrounding the thermonuclear core, dispersing plutonium and enriched uranium over several square kilometers of agricultural land. Radiological contamination affected farmland, vegetation and tomatoes, which were the main agricultural product of the area. The government of Francisco Franco and the United States military authorities agreed from the outset to manage the incident with the greatest possible discretion, minimizing the information available to the Spanish population. The 4th bomb fell into the sea. Its location proved enormously more difficult than that of the 3 on land. The United States Department of Defense mobilized a fleet of more than 30 vessels and Navy submarines, as well as specialized diving teams, to scan the seabed. Initial searches focused on the immediate coastal area, but reconstructions of the fall trajectory were complicated by the absence of precise eyewitnesses in the water. It was a local fisherman, Francisco Simo Orts, known as Paco el de la Bomba, who provided the most valuable information. He had seen something fall into the sea and remembered the point with the precision typical of fishermen who know their fishing grounds. The bomb was finally located on the 15th of March, 1966, at a depth of approximately 870 meters, after weeks of searching. Its recovery was carried out by the unmanned submersible vehicle Alvin and the CURV recovery system of the United States Navy. The process lasted until April 7, nearly 3 months after the accident. The handling of the incident revealed both the operational capabilities of the U.S. Navy in deep-sea search and recovery and the limitations of informational transparency in democratic states when nuclear security matters are involved. The long-term consequences of the Palomares incident were not limited to the recovery of the bombs. Plutonium contamination on land was partially remediated in 1966 by removing tons of contaminated soil that were transported to the United States for permanent storage. However, the most contaminated areas were not completely cleaned, and decades later, there was still scientific debate about residual levels of radiological contamination in the subsoil of Palomares and in the adjacent coastal waters. Spain and the United States reached an agreement in 2010 to complete the cleanup of the area, formally committing to remove the remaining contaminated soil. However, the implementation of the agreement has been delayed for years due to political, diplomatic, and budgetary reasons. The most recent estimates by Spanish radiological protection agencies conclude that residual contamination does not represent an acute health risk for the current inhabitants of Palomares, although plutonium levels in certain areas remain above the limits established for unrestricted use zones. The Palomares incident is part of a series of nuclear accidents linked to the Continuous Airborne Alert Program of the United States Air Force, known as Operation Chrome Dome, which kept aircraft carrying nuclear weapons in constant flight during the Cold War. Other similar accidents occurred in Thule, Greenland, in 1968, and in the English Channel in 1956. The Mediterranean, used as transit airspace for these missions, unknowingly hosted for years a threat whose true magnitude was only understood when the accident made visible what had, until then, been completely secret. No sea in the world has generated a mythological corpus comparable to that inspired by the Mediterranean in the civilizations that surrounded it. For Greeks, Romans, Phoenicians, Egyptians, and Mesopotamians, the sea was not simply a geographical space for communication or resources. It was the domain of supernatural beings that determined the fate of those who dared to cross it, a boundary between the ordered world and primordial chaos, and an inexhaustible source of narratives that attempted to make sense of phenomena that empirical observation could not explain. In archaic Greek cosmology, the sea was presided over by Pontus, a primordial deity that emerged directly from the original chaos, and by his descendants, among whom were Nereus, the truthful and benevolent old man of the sea, Phorcys, father of monsters, and Ceto, personification of the dangers of the deep ocean. These beings of the archaic marine pantheon were gradually displaced in importance by Poseidon, son of Cronus and brother of Zeus, whose trident controlled earthquakes, storms, and currents. The association between Poseidon and earthquakes was consistent with the observation that Mediterranean coastal areas were frequently shaken by seismic activity, a phenomenon that the Greek mind logically connected with the power of the sea god who stirred the waters from below. The sea monsters of Greek mythology in many cases have a precise Mediterranean geography. Scylla and Charybdis, the two creatures that threatened sailors in the Strait of Messina, according to the account of the Odyssey, can be interpreted as personifications of the real dangers of the passage. The opposing currents between the Tyrrhenian and Ionian seas, the whirlpools that form under certain tidal and wind conditions, and the rocky outcrops that make navigation near the coast dangerous. The Strait of Messina is, in fact, one of the points of greatest hydrodynamic complexity in the Mediterranean, with currents that periodically reverse direction, and with the occasional generation of small whirlpools that surprise light vessels. Homer's Odyssey is essentially a mythical geography of the Mediterranean. The journey of Odysseus from Troy to Ithaca, which in direct geographical terms should take only a few days of favorable sailing, becomes a 10-year voyage through seas and lands, that scholars have attempted to identify with real Mediterranean locations. The land of the lotus eaters has been proposed on the north coast of Africa. The land of the Cyclopes is sometimes placed in Sicily. The island of Circe is identified with the promontory of Circeo in the Italian region of Lazio. The land of the Phaeacians has candidates in Corfu and in other islands of the Adriatic or Ionian seas. These identifications are speculative, and almost none enjoys academic consensus, but they reflect the deep connection that the Greeks established between the narrative space of myth and the real geography of the sea they navigated. For the Romans, largely heirs to the Greek pantheon, the Mediterranean also had a specific symbolic dimension. The name Mare Nostrum, our sea, with which the Romans designated the Mediterranean at the height of the empire's expansion, reveals a conception of the sea not as a frontier, but as the interior of a unified political and cultural space. Rome had expanded to completely surround the Mediterranean basin, and the sea that washed its provinces was perceived as the center of that shared space, not as its boundary. Phoenician mythology contributed its own oceanic figures to the Mediterranean imagination. Yam, the Canaanite sea god, was a primordial deity associated with chaos and disorder, who in the texts of Ugarit appears in conflict with Baal, the storm god. The myth of the confrontation between Baal and Yam can be read as a metaphor for the relationship between coastal populations and the sea that dominates their lives. Threatening and destructive when out of control, but tameable and useful when the civilizing hero manages to impose limits. The Egyptian god of the sea, Seth, shares with Yam a certain connotation of chaos and violence, although in the Egyptian pantheon his figure is more ambivalent. Seth is the god of the desert and storms, but also of the outer sea, the sea that the Egyptians called Wajwa and identified with the northern Mediterranean. Representations of Seth as a marine animal or as an aquatic force appear in certain ritual contexts of Ptolemaic Egypt, when contact with the Greek world was enriching the iconographic repertoire of Nile culture. The biblical tradition also maintains an ambivalent relationship with the sea that reflects the geographical position of Israel on the eastern edge of the Mediterranean. For the Hebrew peoples of the Bible, the sea is fundamentally the Tihom, the great primordial abyss, the chaotic waters over which the Spirit of God moved before creation, according to the account of Genesis. This conception of the sea as preordered chaos has direct parallels with Mesopotamian cosmology, where the primordial saltwater, Tiamat, must be defeated by the ordering God for the cosmos to exist. The Book of Jonah is the biblical narrative most directly linked to the Mediterranean as a geographical and symbolic setting. Jonah, a prophet of Israel, receives the divine command to go preach in Nineveh, the great Assyrian city, and flees in the opposite direction by embarking in Jaffa, the Mediterranean port known today as Jaffa on the Israeli coast, bound for Tarshish, generally identified with the area of southern Spain, possibly Huelva or Cadiz. The flight leads Jonah to the heart of the Mediterranean, where a great storm threatens to sink the ship. The sailors, from different origins and worshippers of different gods, recognize in the storm a supernatural manifestation, and, after casting lots to determine who is responsible, throw Jonah into the sea. What follows is one of the most well-known narrative episodes in world literature. A great fish, Dagon Gadol in the original Hebrew, swallows Jonah. The prophet remains inside the fish for 3 days and 3 nights, during which he prays to God and is finally vomited onto dry land. Later Christian tradition identified the great fish as a whale, an association that has persisted in the popular imagination, although the Hebrew text does not specify the species. The account of Jonah in the belly of the fish was interpreted in Christian tradition as a prefiguration of the death and resurrection of Christ, according to the reference that Matthew places in the mouth of Jesus when he speaks of the sign of Jonah. The nature of Jonah's great fish has been the subject of both theological and zoological debate. In the Mediterranean, there are indeed large sharks capable of swallowing a human being, mainly the great white shark, whose presence in the Mediterranean is documented although rare, and the whale shark, whose dimensions are colossal although its diet is filter feeding. The humpback whale and the sperm whale, which do possess stomachs of sufficient size, are occasional visitors to the Mediterranean, mainly in the western Mediterranean. Historical records include several cases of people recovered alive from inside large great white sharks, although the biological plausibility of the story of Jonah, in a literal sense, remains debated. The biblical Great Flood of Genesis has been linked by some researchers to real catastrophic events in the Mediterranean world and the Near East. The hypothesis of Ryan and Pittman, proposed in the 1990s and based on sedimentary data from the Black Sea, posits that the Black Sea basin was a closed freshwater lake until approximately 7,600 years ago, when the rise in the level of the Mediterranean would have surpassed the Bosporus threshold and triggered a catastrophic flooding of the lake basin. The magnitude of the event, with millions of square kilometers of Black Sea coastal lands submerged in a relatively short period, would have profoundly impacted the Neolithic populations of the region and could have left a mark on the cultural memory of different peoples, including the ancestors of biblical and Mesopotamian traditions. The hypothesis has been partially corroborated by some sedimentary and archaeological data from the Black Sea, but it has also received significant criticism from geology and archaeology. The speed of the flooding proposed by the original model appears excessive according to more recent evidence, and the reconstruction of the Black Sea level during the period in question remains a matter of debate. However, the existence of a significant marine transgression in the Black Sea around that period is accepted by most specialists, although its exact dimensions and speed are uncertain. References to the sea in the rest of the Hebrew Bible are constant and not always negative. The Psalms celebrate the majesty of the sea as a work of divine creation. The Book of Job describes marine creatures of mythological dimensions: Leviathan, the great sea monster, and Behemoth, the beast of the marshy waters. The identification of Leviathan with a real biological species has generated proposals ranging from the Nile crocodile to the sperm whale, including various species of whale or shark. Scholars of the Old Testament today tend to interpret these creatures as personifications of primordial chaos rather than as references to specific animals, but the connection between biblical sea mythology and the real fauna of the Mediterranean and its adjacent waters is inevitably suggestive. The Mediterranean generates and amplifies highly intense meteorological phenomena that have shaped the history and perception of the sea in the cultures that surround it. The best known of all is the sirocco, the warm wind laden with Saharan dust that rises from North Africa, crosses the central Mediterranean, gaining humidity over the warm waters, and reaches the Italian, Greek and Dalmatian coasts as a humid and suffocating wind. The sirocco can raise coastal temperatures by several degrees in a few hours, transport sand particles from the Sahara that tint the sky red and generate colored rains, and alter patterns of human behavior in such a measurable way that in various historical legislations it has been considered a mitigating circumstance in minor crimes. The Mistral, the northern wind that descends through the Rhone corridor toward the Gulf of Lion, has effects opposite to the sirocco: dry, cold and violent. It can reach speeds of 100 kilometers per hour and raise waves several meters high in the western Mediterranean, even in the absence of low-pressure systems. The Mistral is the main cause of the intense vertical mixing that occurs in the Gulf of Lion during the winter months, the process that generates dense Mediterranean water that then circulates toward the depths of the entire western basin. Without the Mistral, the thermohaline circulation of the western Mediterranean would be fundamentally different. Medicanes, an acronym for Mediterranean hurricanes, are tropical or subtropical cyclones that form over the Mediterranean under conditions of great atmospheric instability, normally in autumn, when the sea still retains summer heat while the continental air has cooled. Although less intense than Atlantic hurricanes or Pacific typhoons, medicanes can reach sustained winds of 100 to 130 kilometers per hour and cause extreme rainfall, storm surges, and considerable damage in coastal areas where they make landfall. The Medicane Ianos cyclone of 2020 and the Daniel cyclone of 2023, which caused devastating floods in Libya with thousands of victims, are recent examples of the intensity these systems can reach. The relationship between extreme Mediterranean meteorological phenomena and global warming is an active field of research. The most recent climate models suggest that the total number of medicanes could decrease, but that those that do form will on average be more intense as a consequence of higher sea temperatures. Extreme autumn rainfall events, such as the Dana that affected Valencia in 2024, are being linked by climatologists to the increase in the surface temperature of the Western Mediterranean, which acts as a source of energy and moisture for the storms that form or intensify over its waters. One curious aspect of the Mediterranean is that it is one of the seas with the greatest volcanic activity on the planet. Its location in the convergence zone between the African and Eurasian plates generates a complex tectonic geometry that favors both island arc volcanism and intraplate volcanism. The Aeolian Arc, formed by the islands of Stromboli, Vulcano, Lipari, Panarea, Salina, Filicudi and Alicudi in the southern Tyrrhenian Sea, is the most studied active volcanic system in the Mediterranean, and one of the best monitored in the world. Stromboli is a singular case, even in the global volcanic context. The volcano has been erupting almost continuously for at least 2,000 years, with regular explosions that eject pyroclastic material from its crater at a frequency that has led volcanologists to call it the lighthouse of the Mediterranean. The regularity of its eruptions was used by ancient navigators as a nighttime positional signal. In 2019, an unusually violent paroxysmal eruption generated an ash column several kilometers high and triggered a small tsunami that reached the coast of Sicily. The Panarea submarine volcanic field, also in the Aeolian Arc, presents active submarine fumaroles at shallow depth. In November 2002, a sudden degassing event generated a column of bubbles and gases that emerged in the coastal area of the island, creating an effervescent foam that spread for kilometers. The episode caused no casualties, but demonstrated the persistent activity of the submarine hydrothermal fields of the southern Tyrrhenian. The island of Santorini, in the Aegean, is the setting of what was probably the most catastrophic volcanic eruption in the Mediterranean in the last 4 millennia. The Minoan eruption, dated to around 1628–1600 BC, according to the different available calibrations, destroyed the island of Thera and generated an ash column visible throughout the eastern Mediterranean. The volume of material expelled is estimated at several tens of cubic kilometers, and the resulting tsunami wave must have reached the coasts of Crete, mainland Greece, Anatolia and the Levant with waves of potentially devastating heights. The connection between the Santorini eruption and the collapse of the Minoan civilization has been proposed and debated for decades. Although most current specialists consider that the end of Minoan culture was a more complex and prolonged process than one caused by a single catastrophic event. The Empedocles submarine volcano in the Strait of Sicily is another focus of active volcanism. Its periodic eruptions have generated throughout history ephemeral islands that briefly appear above the surface before being eroded by the sea. The last appearance of the island, known as Ferdinandea or Graham Island depending on the nation that claimed it at each moment, took place in 1831. The island emerged as a result of a submarine eruption, was simultaneously claimed by the Kingdom of the Two Sicilies, France, Spain, and the United Kingdom, and disappeared beneath the waves before any of the powers could establish a permanent presence on it. Today, The submarine volcano lies just a few meters below the surface and is closely monitored by Italian volcanologists. But the geography of the Mediterranean is not only a passive stage of human history, it is one of its main drivers. The possibility of sailing from coast to coast without losing sight of land for most of the year, the regularity of seasonal winds that allow predictable routes to be traced, the abundance of bays, natural harbours and islands that offer shelter and stopover, and the concentration of marine and terrestrial resources along its coasts turned the Mediterranean into the axis around which the first complex civilizations of the West and the Near East revolved. The Phoenicians were probably the first navigators to mentally map the Mediterranean as a unit. Departing from their cities of the Levant, Tyre, Sidon, and Byblos, they established trade routes that reached as far as the Atlantic and founded colonies in North Africa, in Sicily, in Sardinia, in southern Spain, and in the Balearic Islands. Carthage, founded according to tradition in 814 BC on the Tunisian coast, became the hegemonic power of the Western Mediterranean for centuries, controlling the routes that connected the West with the East through the Strait of Sicily. The Punic Wars between Rome and Carthage, which took place between 264 and 146 BC, were essentially a dispute for control of the Mediterranean Sea and its trade routes. The naval battle of the Aegates Islands, fought in 241 BC off the western coast of Sicily, was the decisive confrontation that determined the end of the First War and the beginning of Roman hegemony at sea. In 2017, underwater archaeologists recovered in the Aegates area several bronze rams, the bow rams of the triremes that fought in that battle, constituting the most direct archaeological evidence of a naval engagement of classical antiquity. Mediterranean trade in the Roman period moved volumes of goods that were not matched again in the Mediterranean until the 18th century. Amphorae of oil, wine and garum circulated from Hispania, North Africa and the Aegean basin toward Rome and toward the major consumption centers of the empire. The lead-sounding weights used to calibrate depth lines on Roman ships appear in Mediterranean shipwrecks with the same regularity as amphorae, evidencing a navigation of caution and systematic knowledge of coastal seabeds. The fall of the Western Roman Empire did not mean the end of Mediterranean maritime traffic, but rather its reorganization. The Byzantine Empire maintained for centuries control of the eastern Mediterranean and partially of the Central Basin. The Arabs, after their expansion across North Africa in the 7th century, became a Mediterranean naval power and temporarily controlled Sicily, Crete, Sardinia, and several coastal areas of the Iberian Peninsula and Italy. The later hegemony of Venice and Genoa in the Middle Ages transformed the Mediterranean into the most sophisticated financial and commercial system of the pre-Columbian world, with navigation, accounting, maritime insurance and diplomacy techniques that anticipated by several centuries the institutions of modern capitalism. The Mediterranean hosts approximately 7% of all known marine species on the planet, despite representing less than 1% of the global ocean surface. This disproportion between surface area and biodiversity makes the Mediterranean one of the most important marine biodiversity hotspots in the world, comparable in relative terms to tropical ecosystems such as the coral reefs of the Indo-Pacific. Among the emblematic species of the Mediterranean stands out Posidonia oceanica, the marine phanerogam that forms extensive underwater meadows in the shallow waters of the entire western and central basin. Posidonia is not an alga, as is often mistakenly believed, but a flowering plant fully adapted to underwater life. Its meadows are one of the most productive and most threatened ecosystems of the Mediterranean. They produce oxygen, stabilize sediments, constitute breeding habitat for dozens of species of fish and invertebrates, and act as a carbon sink. Posidonia meadows are also extremely long-lived. Genetic analyses of some specimens in the western Mediterranean suggest that certain living plants could be thousands of years old, which would make them some of the oldest known organisms on Earth. The Atlantic bluefin tuna, Thunus thinus, spends a crucial part of its life cycle in the Mediterranean. Adults migrate from the North Atlantic to the spawning areas of the Balearic Sea, the Tyrrhenian, and the central Mediterranean during the spring and summer months. The species was for centuries one of the most important fishery resources of the Mediterranean, the object of a capture and processing industry that left archaeological traces from classical antiquity to the 20th century. The almadrabas, fixed net systems that intercepted tuna along their migratory routes, operated in the Strait of Gibraltar, on the Andalusian coast, and in the Tyrrhenian for millennia. Overfishing in the 20th century dramatically reduced populations, and although management measures adopted in the last 2 decades have allowed some recovery, Mediterranean bluefin tuna remains a vulnerable species. The bottlenose dolphin, the harbour porpoise, and the long-finned pilot whale are the most frequent cetaceans in the Mediterranean, although the basin also receives periodic visits from fin whales, sperm whales, and, less frequently, blue whales. The Pelagos Sanctuary, established in 1,999 inches the northwestern Mediterranean between France, Italy, and the Principality of Monaco, is the first multinational marine protected area in the Mediterranean, created specifically to protect cetaceans. Its 87,500 square kilometers encompass some of the most productive zones of the Western Mediterranean, where the upwelling of deep, nutrient-rich waters sustains a highly complex trophic chain. Threats to the Mediterranean have accumulated over decades. Overfishing affects most commercially important fishery resources. Plastic pollution, which enters the sea through rivers, coasts, and maritime activities, has reached alarming concentrations, especially in convergent zones of currents, where plastic debris tends to accumulate. The Mediterranean, with its semi-enclosed currents that do not freely connect with the great ocean gyres, has a lower dilution capacity than open oceans, which causes pollutants to remain in the basin for longer periods. Water warming is perhaps the most far-reaching threat. Surface temperatures of the Mediterranean have increased between 0.5 and 1 degree Celsius in recent decades, with the most conservative projections anticipating additional increases of between 1 and 3 degrees by the end of the 21st century, depending on different emission scenarios. This warming is favoring the expansion of invasive species of tropical origin that enter the eastern Mediterranean through the Suez Canal, the phenomenon known as Lessepian migration. Fish such as the silver-cheeked pufferfish, the golden silago, or the lizardfish, are now abundant in the eastern Mediterranean and are altering trophic chains of ecosystems that did not evolve in the presence of these competitors. Ocean acidification, a consequence of the absorption of additional atmospheric carbon dioxide, particularly threatens calcifying organisms, corals, mollusks, sea urchins, and a multiplicity of planktonic microorganisms whose calcium carbonate shells or skeletons dissolve more easily in more acidic waters. The red coral, Corallium rubrum, which thrives on rocky walls of the shallow and semi-dark Mediterranean, has declined significantly in recent decades due to the combination of overexploitation for the jewelry industry and warming that causes bleaching events similar, though smaller in scale, to those that devastate tropical reefs. Despite millennia of navigation, decades of oceanographic exploration, and centuries of historical and archaeological research, the Mediterranean holds secrets that contemporary science has not yet managed to reveal. The complexity of its seafloor, the richness of its historical record, the density of its ecosystems, and the uniqueness of its physical and geological processes generate a list of unknowns that is continually renewed. Submarine mapping of the Mediterranean, although much more advanced than that of the great oceans, remains incomplete in the deepest areas. Current bathymetric models have acceptable resolution for continental shelves, but the abyssal floors of the Hellenic Trench and of some deep basins of the central and eastern Mediterranean have not been mapped with the precision necessary to detect small-scale geological structures, hydrothermal fluids, or topographic anomalies that could indicate archaeological sites or unknown ecosystems. The exact distribution and extent of brine ecosystems in the eastern Mediterranean is another active field of research. Known brine lakes and rivers are probably the visible part of a more extensive system of hypersaline fluid seeps linked to Messinian salt diapirs. Systematic surveys with autonomous underwater vehicles in the deepest parts of the eastern basin could reveal new chemosynthetic ecosystems of enormous biological interest. In the field of underwater archaeology, the continental shelf of the southern Mediterranean, from Morocco to Egypt and the Levant, has barely been systematically explored. The combination of dense coastal populations during the Neolithic and the Bronze Age, the rise in sea level since the last glacial period, and the documented presence of very ancient trade routes between Egypt, the Levant, and the central Mediterranean creates objective conditions for the shallow seabeds of these coasts to contain evidence of settlements, exchanges, and shipwrecks that have no equivalent in current records. The Messinian salinity crisis itself raises questions that science has not definitively answered. The exact speed of the Zanclean refilling, the precise magnitude of desiccation in the eastern basin, the extent of ecosystems that survived in hypersaline residual basins, and the possible connections between surviving Messinian fauna and current Mediterranean biodiversity are open questions. Advances in geochemical analysis techniques, numerical modeling, and the acquisition of new sediment cores from deep zones will be able to provide answers in the coming years. The dynamics of mesoscale gyres and their role in the Mediterranean biogeochemical cycle under climate change conditions is another priority research area. Current climate models predict significant changes in Mediterranean thermohaline circulation throughout the 21st century, but the spatial and temporal resolution of these models remains insufficient to accurately anticipate how local ecosystems will evolve. The seismic and historical record of the Mediterranean includes references to tsunamis generated by earthquakes in the Hellenic Arc, in the Anatolian Fault, and in other active tectonic systems of the basin. The tsunami that followed the earthquake of 365 AD in Crete devastated the coasts of the eastern Mediterranean from Alexandria to the Adriatic, with waves that penetrated kilometers inland. The precise characterization of tsunamigenic sources in the Mediterranean and the assessment of risk for today's densely populated coasts is a field of applied research of urgent priority. One of the most fascinating chapters that the Mediterranean still has to write is that of its own history as an object of knowledge. The sea that saw the birth of the first scientific traditions of the West, that inspired the first maps, the first naturalistic descriptions, the first historical chronicles, remains in the 21st century, a system whose complexity exceeds the instruments available to fully understand it. Each oceanographic expedition, each underwater excavation, each analysis of sediment or environmental DNA adds pieces to a puzzle that grows at the same rate at which it is completed. From the 5,267 meters of the Calypso Deep to the Posidonia Meadows illuminated by the sun in shallow coasts, from sapropels that record extinct climates to shipwrecks that guard objects made 3,000 years ago, the Mediterranean contains in its waters and on its seabed an encyclopedia that science has barely begun to decipher.